In this problem, we're going to turn our attention to using the mesh current method to solve circuits. This circuit right here is a pretty straightforward circuit that we can solve using the mesh current method. The first step in the mesh current method is to identify the meshes of the circuit, indicate those on the circuit diagram, and mark an assumed direction for current flow. Okay. In this circuit, which you have seen in your handouts, we have three meshes. There are no special conditions, so what we're going to need here are three mesh current equations. We'll talk about special conditions in a different example. So since I have three meshes, I'm going to go ahead and determine what those meshes are, give them a label, and make an assumed direction of current flow. The first one that's easiest to deal with is right here. We have a positive 5 volts from this point to this point. So we're going to assume that current is going to flow through this mesh, which is the smallest loop in a circuit, in this direction. And I'm going to call that current I sub A. Next, I'm going to move up here. Since we don't have any power supplies in this mesh right here, in this small loop, we don't have any preference as to which direction the current we're going to assign to the unknown current. So what I'm going to do is I'm going to arbitrarily choose, and I'm going to choose that it's going to be in the clockwise direction. I'm going to label this unknown current IB. And we have a similar situation right here. We have no independent power supplies or dependent power supplies in this circuit, so we're going to have to make an arbitrary choice for an assumed direction of current flow. And I'm going to call that I sub C. Again, we have three meshes, so we need three mesh current equations to solve this circuit. When we're using the mesh current method, we always start off with Kirchhoffs Voltage Law. Right? And Kirchhoffs Voltage Law for any mesh says that the voltages around a closed loop must all sum to 0. So we're going to start off working with mesh A. All right, so mesh A, we're going to invoke Kirchhoffs Voltage Law, which says that all of the potentials around this loop must sum to 0. Across here, across this independent 5 volt supply, we have 5 volts of potential being developed. So 5 volts will be, a positive 5 volts will be developed. Across resistors, we get a potential drop. So that is going to reduce that 5 volts. And we're going to write the potential drop across R2 as being the voltage drop V sub R2. We also have a potential drop across R4. So VR4, when we put all of those together, they must sum to 0 volts. Now I'm going to use Ohm's Law to rewrite these voltages in terms of the currents, in terms of the mesh currents IA, IB, and IC that we have established right here. From Ohm's Law, we know that the voltage across the resistor R2 must be equal to the current that's flowing through R2 plus, we know that the voltage developed across resistor R2 must be equal to the current through resistor R2 multiplied by its resistance. So now to write that current through R2 in terms of the mesh currents that we've established right here, we're going to have to denote the directions of current flow. Through resistor R2, IA is going to flow from left to right because of our assumed directions. And current IB is going to flow through resistor R2 in the opposite direction. So when we're writing this total amount of current, we always want to assume that the mesh that we're working with is the dominant current flow. So I'm going to write that current first. Since IA goes from left to right and IB goes from right to left, we know that based on our assumed directions, IB is going to reduce the total amount of current flow through resistor 5 from the current IA. So that is going to subtract from the current IA. So I write the current through R2 as IA minus IB, multiplied by the resistance of element 2. right, which we can rewrite again as IA minus IB multiplied by 5 ohms. Again, we're going to apply a similar procedure using Ohm's law to determine the voltage across resistor 4. We can write that again as being the current flow, the sum of the currents, and again we're going to assume that IA is the dominant current, so that flows from top to bottom based on our assumed clockwise current flow direction. And IC we assumed is flowing in the clockwise direction as well, so that will flow from the bottom to the top of resistor R4. So that's also going to serve to reduce the total amount of current through R4. So I will give that a negative sign, and we can write the total current as being mesh A minus the current through mesh C multiplied by the resistance of R4, or IA minus IC times 26 ohms. Okay. So now I can combine these two back into my original equation, which would give me 5 volts minus IA minus IB quantity multiplied by 5 ohms minus IA minus IC times the 26 ohms. Must all sum to 0. And again, I'm going to algebraically rearrange this equation, recognizing that we are going to ultimately need a matrix solution here. So when I do that, first thing I'm going to do is I'm going to rewrite this as IA minus IB multiplied by 5 ohms plus IA minus IC multiplied by 26 ohms is equal to 5 volts. And now I'm going to collect like terms, so I can write 31 ohms times IA minus 5 ohms times IB minus 26 ohms times IC is equal to 5 volts. So this becomes one of the mesh equations that we're going to need to get to this final solution. Next, I'm going to turn my attention to mesh B. And we're going to again apply Kirchhoffs Voltage Law. So on mesh B, we're going to have a potential drop across resistor 1, resistor 3, and resistor 2. But we have no independent or dependent voltage supplies or current supplies in this mesh. So the voltage drop across resistor 1 plus the voltage drop across resistor 2 and the voltage drop across resistor 3 must all be equal to 0. Okay. The voltage drop across resistor 1 is fairly straightforward because the only mesh current that is flowing through resistor 1 is IB. So that we can go to directly and say that the voltage is equal to the current times the resistance, which is going to be IB multiplied by 30 ohms of resistance. Now I'm going to look at resistor 2. What is the potential difference across R2? Since I'm looking at mesh B, I'm going to consider that current B is my dominant current. This flows from right to left according to our assumed direction, and IA flows from left to right. So that serves to reduce the current through R2, and I'm going to multiply that by the 5 ohms of resistance of R2. And I'm going to apply a similar procedure when we're looking at R3. Again, IB is flowing from right to left. IC, based on our assumed direction, is from left to right. So IC is going to reduce the total amount of current based on our assumed directions. And that is going to be multiplied by 90 ohms. All of that must sum to 0, and then I'm going to do some rearranging to collect like terms. When I do that, I wind up with negative 5 ohms multiplied by IA plus 125 ohms times current IB minus 90 ohms times current IC. All right, so this becomes our second mesh equation that we're going to need to use. Now we'll turn our attention to mesh C. Okay, again, we will invoke Kirchhoffs Voltage Law. And Kirchhoffs Voltage Law tells us for mesh C that the potential drop across R3 plus the potential drop across R5 plus the potential drop across R4 must all sum to 0 in this mesh. And again, we'll use our current analysis and use Ohm's law to change these potential drops and write them in terms of the unknown mesh currents. So for R3, again, since we're working with mesh C, we're going to assume current C to be the dominant one. So IC flows from left to right, IB flows from right to left, so that's going to serve to reduce or subtract from the total current flow through R3. That will be IC minus IB multiplied by the 90 ohms of resistance of R3. Through R5, the only mesh current that flows is IC, so IC times R5, which is 8 ohms, will give us the potential drop across R5. And the potential change across R4, again, we're going to assume that IC is the dominant current. IC flows up. IA also flows through R4, and it flows down. So those are in opposite directions from each other. So IA will reduce that. And we need to multiply that by the 26 ohms of resistance. All of that must sum to 0. Right? Again, I will rearrange this equation to group like terms, and we'll get 26 ohms times IA minus 90 ohms times IB plus 124 ohms times IC is equal to 0. And this becomes our third independent mesh equation. So now if we look at all of the equations that we've developed, for each of the meshes, we have a total of 3 independent mesh equations and 3 unknowns, IA, IB, and IC. Again, we can solve these 3 equations simultaneously using matrix algebra methods. And when we solve them simultaneously, we should get a result of the current through A being 0.3125 amps, IB being 0.125 amps, and IC being 0.15625 amps, which we usually rewrite in terms of milliamps. So this would be 312.5 milliamps, 125 milliamps, and 156.25 milliamps. Again, in summary, what we've done here is we have identified the meshes of the circuit. Using Kirchhoffs Voltage Law, we've said that the sum of all of the potential increases and decreases around the mesh must sum to 0. We've used Ohm's law to rewrite all of those potential drops in terms of the unknown mesh currents. And we've developed 3 independent equations that could be solved simultaneously to determine all of the currents in the entire circuit. Now that we've determined all of these currents, we can also combine them together to determine the total potential difference across each of the resistors and determine the potential difference at each node in the circuit as well. So we now know everything about the circuit, and we've completely solved the circuit using the mesh current method.